Hello everyone. In previous lecture we discussed the chiral proline base reaction. In today's lecture we discuss the alkaloid base reaction. In alkaloid base reaction, first the conjugate addition reaction. For conjugate addition reaction, the different types of alkaloids are used, in which the cinchona alkaloids are a large class of compound and it is extracted from the bark of homonium trees. It is cultivated in equatorial climatic zone between the Bolivian and Venezuelan ends and Indonesia. In the extract of the bark present more than 30 alkaloids having proportion 5 to 15% weight by weight. Out of these 4, they represent 50% of the alkaloid such as quinine, and it is represented as QN, quinidine that is QD, cinchonidine that is CD, and cinchonin that is CN. Here mentioned in scheme number 1, this is the structure of a quinine molecule or quinine alkaloid QN. This is QD, that is quinidine. Okay, now then CD, that means the cinchonidine, and here CN, that means the cinchonin. That means this is a bifunctional alkaloid base organocatalyst. Now the QN that means the quinine, is the most well-known alkaloid and it is used as anti-malarial drug over a 400 years until the chloroquine discovered, while the QD, that means this QD, that is quinidine, is used as the anti-arithmetic agent. And in chemistry, all these compounds, that means the QN, QD, CD, and CN, are used as a cheap chiral source. And these molecules, that means the QN, QD, CD, CN, these molecules, they activate the nucleophile by enamine and carbanium formation and electrophile via hydrogen bond. That means this quinine, quinidine, cinchonin, and cinchonidine, they activate the nucleophile by enamine and carbanium formation and electrophile via hydrogen bond formation. And these compounds, they are the diastereomer having the 5 stereogenic centers. That means this 5 stereogenic center, 1, 2, 3, 4, 5. 5 stereogenic centers, and the chiral quinacridine, the nitrogen, is the most important and it is responsible for the direct transfer of chirality during the catalysis. That means this nitrogen is the most important role. It direct transfer the chirality during the catalysis. Now the quinine versus quinidine and cinchonidine versus cinchonin has opposite absolute configuration, and this means that uh, that the very often this pair of diastereomer, it acts as the enantiomer at the C9 position. C9 position, that means here the C9 OH group. Okay, it acts as the Bronsted acid. Bronsted acid, that means the which gives the H plus. Okay, so the acid base coexist in this molecule, and it is possible to activate both the nucleophile and the electrophile simultaneously to use as a bifunctional organocatalyst. And here the mention in scheme number 2, here this is the, that means this OH, quinidine containing OH, and here QN contain, that means quinine, here quinidine and here quinine structure, and this OH here activate the electrophile. Now what about the nitrogen? Here nitrogen, it activate the nucleophile. That means this is the most important. I have already tell the quinidine, quinine, cinchonin, and cinchonidine, they activate the electrophile and nucleophile. Okay, therefore here this OH containing quinine and quinidine activate electrophile, and here from this nitrogen here activate the nucleophile. That means this is the dual activation modes by bifunctional basic QD and QN organocatalyst. Now the catalytic asymmetric 1,4 addition. 1,4 addition of these thiols to the cyclic enone with modified cinchona alkaloids has been demonstrated in scheme number 3. Here the Michael products can be isolated with high yield of initio selectivity for the range of substance. Here L1, that means this catalyst is used, and here a simple Michael addition reaction 1,4 addition will be take place. This H, it will be attack here. Okay. Now then this bond will be localized. We know the mechanism. It is a simple Michael addition reaction or the 1,4 addition reaction, and here we get the product. Here that means this scheme number 3 is the initio selective Michael addition of thiophenols to enone. And later on, the Tandem Michael aldol reaction has been developed for the preparation of medicinally important the chiral thiochromes. The scheme number 4 mentioned, that means in next slide. And here the new 1 pot process with the 1 mole % of the cinchona alkaloid derived thiourea catalyst, that is L2, and which is synergistically activate both the Michael donor and the acceptor. That means this catalyst, this is L2. This catalyst is activate the both Michael, this is Michael donor and this is Michael acceptor. And we know that in Michael addition reaction, one is Michael donor and Michael acceptor. Due to presence of this catalyst here, both Michael donor, this is, and Michael acceptor, it activates, and the rate of reaction will be enhanced. Here this will be the attack here. Okay, and then next it will be delocalized. Here we get the product. That means this is the scheme number 4. Here it is a simple reaction of the 2-mercaptobenzaldehyde. This is the structure of the 2-mercaptobenzaldehyde with alpha beta unsaturated oxazolidinone. Okay, I repeat it, alpha beta unsaturated oxazolidinone. Let me this one. Now similarly, the conjugate addition reaction is also reported by using the catalyst, that means the L3. Okay, this type of catalyst, it is a direct stereo controlled construction of the adjacent carbon or the heteroatom. Substituted the quaternary and tertiary stereo centers from readily available the starting beta keto ester. This is a beta keto ester. Here the scheme number 5. It is simple mechanism, and this overall reaction take place in presence of this EL3, that means this chiral catalyst. Okay, here we know the mechanism. Here first the abstraction of the proton, and here it is simple aldol reaction, Michael addition reaction. Here we get the invalid ion, this will be attack. Okay, and here we get the this one product. Now next, the chiral oxacyclic structure such as the tetrahydrofuran ring are commonly found in the many bioactive compounds, that is the cinchona alkaloids thiourea, that means the L4 catalyst. Okay, and it catalyzes the cycloetherification of gamma hydroxy, that means this one, gamma hydroxy alpha beta unsaturated ketones with the excellent initio selectivity, even with the low catalyst, the loading at room temperature, and the probable activation intermediate might to the transition state. This is actual transition state. Here L4 catalyst, that means this one, it form the complex with this here the NH, that means this 2NH, it will form the complex with this oxygen, and here this will be oxygen, it will be attack here, and here we get the formations of 5-member or the 6-member ring. That means this is the cycloetherification via intramolecular oxy-Michael addition reaction. It it is a Michael addition, but it is the intramolecular oxy-Michael addition reaction. Oxy-Michael addition reaction because here oxygens are involved. Therefore, oxy-Michael addition reaction. Now, the catalyst Diel-4, that means this one. The catalyst Diel-4, this one, can also be catalyzed in the domino, such as Asymmetric Michael reaction of aniline, this one, aniline, and the nitroolefin enolates to afford the chiral 4-amino benzopyrene. That means this one, the formation of benzopyrene bearing two consecutive stereogenic centers, these two stereogenic centers and one quaternary stereogenic centers, and the products can be isolated with high yield of enantiomer selectivity, and this is a simple domino Asymmetric reaction. Now the next, the chiral amine, that means the L5 catalyst, this one, the L5 catalyst has been used to activate the alpha beta unsaturated enone system. This is the alpha beta unsaturated enone system with the nitroalkene. This is the nitroalkene toward the well-defined enamine-iminium activation mode in the presence of the 2-fluorobenzoic acid. You mention here 2-fluorobenzoic acid as an additive. That means it just enhance the rate of the reaction, and the reaction efforts the Diels-Alder adduct. It is a simple Diels-Alder adduct reaction. Diels-Alder adduct during bearing 3 or 4 stereogenic centers with the high enantiomer selectivity, here mentioned in scheme number 8. The extension of this process of other Michael acceptors such as N-benzyl malamide leads to the formations of cyclohexanone to yield enantiomeric excess approximately 99%. That means this is simple reaction. That means this is the asymmetric Domino Michael reaction. Here it is a simple reactions. Here first it will be form this enolate ion, this will be attack, and cyclization will be take place and we get this product. Here again same mechanism. Okay, Michael addition. Now the synthesis of trifluoromethyl substituted to isooxazolines can be accomplished by the domino, that is Michael cyclization dehydration reaction of hydroxylamine, that is NH2OH, with the range of E trifluoromethylated enone derivatives in the presence of the N3,5 bis trifluoromethyl benzyl quinidinium bromide, that means the L6, this catalyst, a chiral phase transfer catalyst. In the L6 catalyst, it is nothing but the chiral phase transfer catalyst, and here we get this type of the product. Okay, this is the synthesis of the trifluoromethyl substituted to isooxazoline. Now, and last one is the aldol reaction. In aldol reaction, this is the cross aldol reaction between the enolizable aldehyde and alpha ketophosphates can be achieved using the 9-amino 9-deoxyepiquinine, that is L7 catalyst. That means this catalyst is used, and the reaction works especially well with the acetaldehyde, which is a tough substrate for the organocatalysis of the cross aldol reaction. Here the simple cross aldol reaction will be take place, and here we get the final product. We know the cross aldol condensation reaction. So friend, never miss a video. Subscribe to my YouTube channel. Okay, thank you.